Hello, this is Norman White, member of the Research Faculty Advisory Group at NYU. This is an introduction to three presentations on big data at NYU. The first one gives the background, that's this one. The next one will talk about the MapReduce processing model and how you actually handle big data and process it. And the third part will be a short discussion on what NYU might be doing with big data and why I think it's important. I hope you enjoy them. Thank you very much. Hello, my name is Norman White. I'm a member of the NYU Research Faculty Advisory Group, and at the last meeting, just at the end, we started to talk a little bit about big data, and there were some questions about exactly what was it, and people had different ideas. And so I was asked next fall to give a little presentation. I then decided why wait till the fall, that I would put together a small PowerPoint presentation and use ScreenFlow to put some video and audio to it and mail it to you so you didn't have to wait until the fall. Because I think that big data is a big deal and that NYU needs to have a name in the game here. But first, some background as to where big data came from. Big data was originated at Google when Google started to develop its PageRank algorithm and realized that basically it had to invert a matrix that was the size of the order of the number of documents on the web. And they really didn't, there was nothing out there that would do that. And also they wanted to store everything on the web, and there really was no storage architecture that would do exactly what they wanted. So they went out and developed their own. And that project has now been cloned and copied in an open source project called Hadoop. And together all these technologies are called big data, NoSQL, terms like that to indicate this new processing and data storage approach. This infrastructure and these techniques, although they started in the search industry, have now moved into finance, entertainment, consumer products, media, hard sciences. They're now being used more and more rapidly in different kinds of industries. This has a number of implications for education. The first of all is that there's a whole new set of problems that you can attack with big data kinds of techniques that you couldn't attack before. Now, so for research, that's a big deal. It means that people in the social sciences now have a tool to attack some problems that they didn't have before, and people in the hard sciences have yet another tool in their tool set to attack some very large problems. In addition, cloud computing allows even small and medium-sized companies and/or organizations or research projects to attack very large problems if they only have to do them once or twice. For instance, the New York Times used Amazon Web Services to scan and index all of its content over a weekend. Actually, it OCR'd it over a weekend and turned it all into text. This makes big data approaches available to a wide variety of companies and organizations. That means that for education, our students need to know some about this. At the end, I'm also going to talk about how one can take some of the large-scale HPC clusters that you find in universities and that we have at NYU and turn them into big data clusters very easily, and how you can expand the capabilities of these clusters to attack more and different kinds of problems. So, well, how did we get here? Well, as I said, we started with Google. They had massive volumes of data, enormous bandwidth requirements. They had availability requirements. They had to be available 24/7, always, never down. Had to be completely fault tolerant. They had many kinds of unstructured data, web documents that have very little structure to them that they wanted to answer questions on. And they had dramatically increasing capacity requirements, again, with no downtime. Had to keep plug new disk in, plug new CPUs in, plug new data centers in, and they had to be globally available. These are fairly major problems to deal with. A single server, not even a single data center, would solve the problem. Had to be an architecture that allows virtually instant increases in capacity. Very unusual, no commercial systems, No database systems could handle it. So they came up with their own architecture and, in particular, a whole new processing approach, or not new, but adapted, known approach. So Larry Page, who designed the original architecture, they didn't have all that much money, so they decided to go, and instead of using commercial servers, build their own data centers out of the cheapest hardware that basically gave them the best performance per dollar, not the highest performance, but the best performance per dollar, and somehow put it together so it was robust and powerful. So they eventually came up with what is called now the Google cluster architecture. And they took hundreds or thousands of commodity PCs, basically held them together, didn't even, in many cases, didn't even put them in a box, but like Velcroed their disk drives onto them, and connected them all together with TCP/IP on the internet. So their first use was search engine indexing and page ranking. And at that point, they had many geographically separated clusters, each of them with thousands of PCs running Linux and running their architecture. If a search request would go to the closest, most lightly loaded cluster, and the domain name servers would figure out which one that was, so they could balance load and stuff. So they relatively rapidly had an architecture that could survive catastrophic events, even at one of their data centers, and not lose any data and keep everything up and running. And we'll see how they did that in just a second. So to process this immense amount of data, Google had to develop ways to parallelize common problems so they could run on its infrastructure. So the two main components they came up with was called the Google File System, which is a distributed file system, somewhat maybe you might think about Lustre or some of those systems, a global distributed file system, and a new kind of processing called MapReduce, which was designed to make it easy to distribute processing across many machines in a way that the system developer didn't really have to think about how to parallelize things. These two components and some others have now been replicated in an open source project called Hadoop and form the backbone of processing at sites like Facebook, LinkedIn, Yahoo, Twitter, of course Google. Now Microsoft has adopted it. Just literally hundreds, if not thousands, of companies are now using this new approach. So what did it look like? They had these problems that they were going to use cheap machines, which weren't going to be reliable. The power requirements were very important, as was air conditioning. And one of the things that both Google and Facebook have done recently is spent a lot of time on how to build really good data centers. So their solution was to design a system so no component's critical. They assume failures will happen, and in fact happen often. They replicate processing across redundant machines. If something dies, if a node dies, a disk drive dies, just unplug it, fix it, replace it, reboot the machine, and that's all you have to do. If a process dies while it's running on a node, or a node gets very slow, so it's getting disk errors or something, just run the process on another machine. Just pick it up, move it, and if the first machine recovers, that's fine. If it doesn't, you've still done the processing. And the critical thing here is the nodes, the machines that have disk on them and processing power, are used both as storage devices and as processing centers. As we'll see, that was a critical part of their architecture. The Google architecture, the file system looks something like this. You take files and you divide them into fixed size chunks, typically 64 megabytes, but that's settable by the user. You distribute these chunks across many machines, typically thousands, so that if you have a huge file, it's across hundreds, if not thousands of machines. You can replicate these chunks, so a file might have a replication factor of 3, which is the default, but maybe you have a file that's accessed a lot, or that you want to make is super redundant, so maybe you say it's replicated 10 times. Typically, the replication will be, if it's 3, there will be 2 replicas in the same rack of a data center, and 1 replica in a different rack, just in case a switch fails. In some cases, they may have a replica in another data center. so that this file is not only triplicated on one data center, but has some copies around the world for very important files. So when chunks are written, they're rapidly sent off to these nodes or chunk servers. And in 1997, when this was started, these were 100 megabit network speeds, and they could write a megabyte in about 80 milliseconds. But nowadays, of course, we have gigabit, 10 gigabit, and 40 gigabit networks. And as we'll see at the end of the talk, that has some major implications, because as the machines get faster and the storage gets faster, the network speeds start to dominate as to how fast you can process things. So the Google file system was then replicated by the Hadoop file system when the Hadoop project came along. I'm going to talk about that in a second. But it's designed, as many of these file systems are, to deliver high aggregate performance to a large number of clients, even though any individual machine may not be that fast. Basic concepts, I've already mentioned some of them. Data is written and read in very large chunks and replicated. Very fast for sequential processing, because what's going to happen in the processing stage is we're going to distribute the programs to the chunk servers or the nodes and run the programs there instead of bringing the data to the programs. Makes a big difference, as we'll see. So the distributed file system was one part of the solution, but the other part, the more interesting one probably, is called MapReduce, and that's their processing model.